So hello, I'm Clément Albinet from MISA, from the Mission Management and Product Quality Division. So I will provide this presentation on behalf of Klaus Kipal, who's the mission manager of the BioMass mission. So the BioMass mission, as it was already introduced by Francesco a few minutes ago, is the 7 Earth Explorer mission, ESA mission, to be deployed in 2023. It will be for the first time a P-band SAR in space, and it will be a fully polarimetric mission. So it's very, very interesting. The first time at ESA, and in general, one of these first type of mission in Europe. And in addition, this mission will be very interferometric and will also allow to do tomography. So I will go more in the detail a little bit further. And the mission is designed to observe forest 8 and biomass. So at ESA, we have three families of missions. So on the left, you can see the science missions that we call the Earth Explorer, that are usually new type of instruments. So we try to explore new type of science. We build instruments that have never been done before, or to observe things that were never observed before. Then we have the second family in blue of the Copernicus mission. So usually these type of satellites are not new type of instruments, and we are building on the continuity of data to provide what we call a service. So for example, for Sentinel-1, the SAR is very similar to the one of Envisat, but was quite similar of the one of ERS. But what is interesting is to have data, to be able to monitor the Earth. And the third family in orange is the meteorological satellites. So that is built and then are usually operated by EUMETSAT. And the biomass mission falls in the science mission, as you can see here. So the problematic why we make this mission is the carbon, the anthropogenic carbon. So as you can see here, you have two different types, main types of sources of carbons. And for the forest, if you can notice here, the uncertainty of the forest are very, very, very high. Why? Because until now, we don't have any mean to measure the carbon which is in the forest. So we derive the carbon from the forest by mean of the carbon that we can measure in the atmosphere, or the carbon that we can estimate in the ocean. So because it's just a subtraction of all the other, let's say, stock of carbons, we have very high uncertainty. And this carbon in the forest is extremely important because it's very close to the human activity. It's a big source and a big sink of carbon. So really the goal of this biomass mission is to address this uncertainty, to be able to measure the carbon in the forest and to greatly reduce this uncertainty and really monitor the flux, the exchanges of carbons that are related to the forest. So what type of information, which information do we need? So we need estimates of forest biomass, forest age, and forest disturbance, for example, to be able to measure when you cut a piece of forest. This information is crucially needed in the tropic because it's in the tropic where most of the deforestation, around 95% of deforestation, appears. And the regrowth, compared to the global scale, is a half coming from the forest. So it's a biomass sink. So it will accumulate the carbon when the forest will grow. And on the other hand, when you cut the forest, you release some carbon. And biomass measurements are needed where the changes occur at the scale of the changes, so 4 hectares. And we need these measurements wall to wall. Means that we don't want only to measure them locally, but we need them globally to have really a global picture of the state of the forest. The accuracy of this measurement should be 20% at 4 hectares, that are similar to the uncertainty that are made when we measure the forest in situ, let's say for ground-based observations. And the deforestation here should be at a smaller scale, a quarter of hectare. And we need several measurements over multiple years to clearly, properly identify deforestation and the regrowth. So how do we measure the forest biomass? So first, the way that you can do it to measure this biomass. So here we talk about dry biomass, so the weight of the dry wood. So the first idea is to go and cut the tree. You cut the tree, you let the wood getting dry, and you weight it. But you can understand that you cannot cut a lot of trees to do that. First, because it needs a lot of time. And then because the main goal of that type of mission is to help protect the forests. So by cutting all the trees, it would not be a good approach. So what we did is that first, there were some different type of trees that were cut and helped to derive some allometry equations, as like the one that you can see here. So that relates the above ground biomass, the biomass out of the ground, to the wood density, the diameter of the trunk, and the forest height. And then in situ, usually you measure the diameter of the trees, you estimate the height of the tree, and thanks to the type of equation with the type of forest that gives you the wood density, you are able to derive an estimation of the above ground biomass. Here you have example of what full polarimetric P-band SAR images look like. And just with your eyes, you can see that you can see different type of elements in the forest. So here, the different color are a combination of polarizations. So you see different type of patterns. You see the river. You see the slope also, which is quite present because this lower frequency will penetrate inside the forest and reach the ground. So the topography can be seen. And it's really, really interesting to see the different effects, the different mechanism, a scattering mechanism within the forest. So it's a very rich information. The concept of the mission is to have one satellite, sun-synchronous orbit, that will operate at P-band, so it's a very low frequency, the lowest for a satellite, SAR satellites, so that will have a wavelength that, contrary to the existing SAR mission, will penetrate up to the ground. There will be two phases in this mission. A tomographic phase, so the first year, where we'll have 6 passes over the same area that will allow to have 3-dimension images, and then interferometric passes from the second year to the end of the mission. I will go more in the details a little bit later. And to have a global coverage achieved every 7 months, and for a mission lifetime of 5 years. So 3 techniques that I will introduce it a bit more later. So SAR polarimetry, polarimetric SAR interferometry, and SAR tomography, knowing that this last method will only be possible during the first year, the first global coverage of the mission. So the requirement for the satellite is a noise equivalent sigma 0. Here you can see lower than 27 dB. You have the total ambiguity ratio, the SSC resolution, 60 meter by 8 meter, dynamic range, radiometric stability, radiometric bias, and crosstalk. I will not go into detail of each of these parameters, but these are really the parameters related to the sensitivity of what you want to measure. And they're extremely important because otherwise you will not be able to see the different changes of biomass and the different changes of the forest itself. Here on the right, you can see a 3D representation of the satellite that has to fit inside the nose of a Vega-C rocket. So the spacecraft today is under construction. So you can see here different pieces. So the body here of the satellite here, another picture of the body of the biomass satellite with here a kind of big umbrella, which is part of the antenna. Here you can see this big umbrella which is deployed. And here you can see the patch antennas that will emit and receive the electromagnetic waves that will be reflected on this big umbrella. So as you can see, it's a new type of technology, so it's related to a lot of challenges. So here you can see a picture with the primary objectives in red, so the tropical forest. You see here also the boreal forest there. You can see also secondary objectives, the ice in the South Pole and desertic area there. Unfortunately, because of the US space object tracking radar, we'll not be able to acquire images over Europe and over the US. So the type of orbit and swath coverage, I said before, it would be sun-synchronous with a 3-day repeat. So between 2 acquisitions over the same area, you will have 3 days. There is only one mode of acquisition for this mission, which is a strip map. So the, let's say, the simple, usual default SAR acquisition mode, where you just cover image over the area. The satellite will have the possibility to roll a little bit. And in terms of coverage, here you can see that we have 3 swaths. So we'll have 3 images over the first swath. The satellite will turn a little bit, 3 images over the second swath, and 3 images over the third swath. So thanks to that, here you can see you will cover these 3 areas. And then the satellite will go up, go down a little bit, and be able to continue to image the other areas. So you will see the same area 3 times, and then you will have to wait 7 months to go again over the same area. And to achieve the global coverage, here you see the 3 paths in green, then the 3 paths in pink, then the 3 paths in blue that we just saw before. You will have this repositioning maneuver I just talked about, and then you will be able to continue to image the following area, etc., etc., until you completely cover the whole globe. And then you go again and you image the same area. So the key challenge is how to estimate the biomass with this system, with this instrument. We have loss of sensitivity of high biomass range. So there is a kind of saturation that appears on SAR system with big biomass. It's even at P-band, so it's one of the challenge. It's the only type of instrument able to really penetrate to the ground in tropical forest, so to really be sensitive to this high biomass, but still you have an effect of saturation. And in addition, you will have environmental factors, so vegetation, soil, rain, wind, a lot of different effects that will have an influence on the SAR signal, will make the SAR signal change even if the forest was stable. So really the goal is to retrieve this biomass, biophysical values of the forest. So we have 3 types of measurements here. So the first one, which is the SAR polarimetric. So the idea is to work on the intensity of the signal. So for example, here you have 1 acquisition with 3 different polarization. And you can see that already the colors are a little bit different where you go. So it means that 1 image with 3 polarization can provide you information about the forest that you observe. So based on this information, especially here, you can see the sensitivity for the HV polarization. You see that this HV polarization changes according to the state of the forest. So after the forest was burned or cut, then the forest is growing and is reaching a kind of maturity. So by using just this information, you are able to estimate in the first way the biomass that you observed. So you can put here a power law relationship between the backscatter and the biomass. And here you can see different type of forests that all follow a little bit that type of law. But what was observed is that by putting an in situ SAR, we could see that the signal of the forest was not stable. So there were changes. Here you can see those small changes that are daily cycles and seasonal changes. So that could be related to the snow, could be related to rain events, could be related to dry and wet seasons in the tropics. It could be related to the different seasons that you have in boreal or temperate forests. You have any effect also of the wind, effect of the environment itself. So only one acquisition could have too high uncertainty. So you need several acquisitions and better methods, let's say, to have a stable and a clear estimate of the biomass forest. of the forest biomass. In addition, here you see different type of vertical spread of the signal at P-band, L-band, and also for LiDAR acquisition. Here LVIS is airborne LiDAR acquisition. So here it's airborne campaign data. And you can see that the same piece of forest is not observed the same way with different frequencies and different polarization. So the forest itself is not seen the same way by different type of instruments. And you see that the scatter vertically are not always spread the same way in the different type of forest. So here you see the coverage, so the canopy, and here you see the ground usually. And you see in different plots, you don't have the same vertical structure of the forest. So biomass, by its strong interferometric configuration, enables new approaches to tackle these problems. And one of these approaches is to remove, let's say, the signal from the ground, which is a big disturbance because the ground can change. You have low topography on the ground. You have effects of humidity of the ground. And with the techniques of the biomass mission, we can remove this ground to really focus on the canopy, which is where the information that we're looking for is. But for that, we need to use techniques that are repeat-based techniques. So polarimetrics are interferometry. And these techniques will allow, like the traditional interferometric techniques, to find a center of phase. So usually with high frequencies, you use the center of phase is at the surface of the ground. But here we have a low frequency. So the center of phase will penetrate inside the forest and will be located within the forest. And by using the different polarization, the center of phase located within the forest for different polarimetry will be located at different altitudes. And using this information that is related to the penetration of the cover, so to the structure of the canopy, will help you, thanks to a model, to retrieve the vertical structure of the forest and then to derive the biomass. So here you see one cell and you see the ground and the canopy. So what we saw a little bit before. And this is possible because we have different observation from different baselines. And finally, during the first year of the mission, we have access to more precious information and mode, let's say, which is tomography. So we use a lot of different baseline acquisition over the same area with a satellite at different position to build in 3 dimensions the forest. So here you have an example from airborne campaign where you have here a metal tower that you can see. So here we just made some slice to observe them because 3-dimension signal is quite hard to represent. And you can see that you can see the different layers of the forest and this metal tower at the different places. So here you can see a little bit of comparison on the different methods. So the 2D SAR, which is using just the polarimetry. Here you have the tomography at the ground level. So when you, from the 3-dimension image, just take the ground level to observe what is on the ground. Here in the middle of the canopy, and here, in the first part of the canopy, lower part of the canopy, and here in the main part of the canopy. And we can see that when you reach the main part of the canopy, your equation, allometric equation between the signal and the forest biomass is improved compared to when you use the whole forest and the whole vertical information. And here you really see the change between the single image and this ground notch, which is a method by using 3 acquisition that aims at removing the ground. So not as precisely as with the tomography, because with the tomography we have much more information on the vertical distribution, but still which is improving compared to using just 1 image. So which information are we going to have will be delivered by the biomass mission? So first, the forest biomass. So it was a requirement, a 200-meter resolution, 1 map every 6-7 months, global coverage of forest area with an accuracy of 20%, or 10 ton per hectare if you are lower than 50 ton per hectare because of this minimum sensibility. Then the forest height, so the height of the forest, the canopy, at the 200 meter resolution, one map here again also every 6-7 months with global coverage and accuracy of 20 to 30%. And finally, disturbances at 50 meter, as we said before, one map every 6 months, global coverage here again, and 90% of classification accuracy. Let's say this is the objective, to reach 90%. So thanks to the tomographic mode that was introduced before, as you could see, we'll be able to reach the ground, so to really see the ground. And by observing only the ground, we could, for the first time, estimate the elevation of the topography, to measure the topography, image the topography below the forest. So all the other type of instruments that we have until now, that are SAR, the wavelength, the wave is absorbed at the top of the trees, so it's not penetrating, it cannot reach the ground in tropical forest. It's the same for most of the LiDAR system, especially the one from space, that there are so many leaves in tropical forest that the signal cannot reach the ground. So we make a big error by estimating the ground. Here, for the first time, we'll have a signal that will reach the ground. So we'll be able to derive the ground below the forest. So this is a kind of secondary objective of the BioMASS mission that we're already working on, is to create a digital terrain model of the ground below the tropical forest. And here you can see an example derived from Airborne Campaign with the Airborne Campaign LiDAR and the Airborne Campaign image below the forest. So the objective is to have a elevation model of 90 by 90 meter with 2 meter 8 accuracy. Another secondary objective is, as we have a wave that penetrates in the, let's say, in the medium in general, we could observe not only the forest, but also the desertic areas. So here you have an area in Tunisia. And if you see with optical images, you see almost only sand. It's hard to separate, let's say, the features in the image. And here you can see a paleo channel. But if you see with L-band SAR, which is already has a kind of penetration from the ALOS mission, you can see that you observe different type of feature here in this paleo channel. So you are able to have a wave that will penetrate in the sand and measure an information below the ground. And at P-band, here you can see measurement by an airborne campaign. You can really see well all the different type of features in the ground. So this can provide really new type of measurements and can open really new type of applications. Finally, in the context of this very innovative mission, we also try to innovate a little bit more on the way we were operating this mission. And so for the first time, in the context of a space mission, we will have all the algorithm of the mission, so used to generate the core products, that will be open source and accessible by everybody. So these algorithms are under definition today, and we set up a project, a Git project called BioPAL for the Biomass Product Algorithm Laboratory. So it's an open source software project, still under development, but which is accessible by everybody. So everybody can go reuse some of this algorithm, let's say. They are very tailored to the BioMASS mission. They're still prototypes, so there may be some bugs, not very optimized in terms of computing time and resources, but it's really something that we are building together with the community, and maybe some of you later will be part of this BioMASS community and will work with us, will support us in this matter, and can work on that type of tool. So they can be downloaded, reused by everybody, modify, and the modification can be proposed to ESA that will integrate it in the core algorithm of the mission. So here you have the QR code and the address where you can go if you are interested in. and join the list of contributors of this project. So as a summary, the BioMASS mission implementation started in November 2013. It was initially proposed in 2005, if I remember well. Today we are closing the phase C, so the critical design review, which is ongoing. So the satellite will soon be almost finished and we'll go in the testing phase. So we are working toward the launch in 2023. So it's still in a few years, but it will come very, very fast. BioMASS is the first P-band SAR and the first radar-ready tomographic mission. So it's a true Earth explorer, because we will see for the first time a big unknown, which is the tropical forest, within the tropical forest and under the tropical forest. And there are still a lot of unknowns and exciting science for that is coming with this mission. It's the first time ESA Earth Explorer mission that will follow an open source approach in the algorithm development. And the new unique vision of Earth from BioMASS will extend beyond forests and into measurements of ice, subsurface geomorphology in deserts, topography, ionosphere, ocean. There are really a lot of fields where this mission could contribute, and we'll discover a lot of new things that we have no idea of. I thank you for your attention.